Hello, this talk is about polynomial-time approximation schemes for Max-CSPs and the notion of Treewidth-Pliability, which we introduced to get such approximation schemes. This is joint work with Miguel Romero and Stan Dezhivny. So let me give an outline of the talk. First, I want to introduce maximization constraint satisfaction problems, the polynomial-time approximation schemes, and the wider contexts, so in particular this diagram on the left. Then I want to discuss sparse techniques, which can be roughly partitioned into those stemming from the Lipton-Tarchin separator theorem and the related notion of hyperfiniteness, and the Baker shifting technique and the related notion of fractional-fragility. Then I move on to dense techniques based on the regularity lemma, and then I will discuss pliability and how it generalizes all that. So first let me discuss the motivation question behind this work. We know that approximation for many problems is easy on planar graphs, but it's hard on some bounded degree graphs. So it's not just the number of edges that makes it easy. And the question is, where is the boundary? What makes planar graphs easy and other graph classes hard? And here by approximation, I mean getting a polynomial-time approximation scheme. So 1 plus minus epsilon approximation in polynomial time, where the degree of the polynomial can depend arbitrarily on epsilon. And the problems I consider are problems such as maximum independent set, minimum vertex cover, max k-cut, and so on. So we could try to formalize this question as follows. Can we characterize graph classes G such that maximum independent set on G has a PTAS? And the trouble with such a question is that there are artificial classes of graphs such as the following. You take any graph G, and you take the union of it with a path of length n, where n encodes the optimum solution to G. Then these graphs are trivial. It's trivial to solve the problem maximum independent set on them, just because we get the solution inside them. However, these are arbitrarily complicated graphs, so there's no structural property that makes it easy. And we will have similar problems even if we assume that the class of graphs is closed to the subgraphs. So this means that we need to look at much more expressive problems. And one way to do that is to look at constraint satisfaction problems in general. So these are problems such as max set, where you are given a formula, you want to assign every variable true or false, and you want to maximize the number of satisfied constraints. Or you have max cut, where you're given a graph, you want to move every vertex left or right in order to maximize the number of edges that go between left and right. Or max 5 coloring, where you have a graph, you want to assign to every vertex one of the 5 colors in order to maximize the number of properly colored edges. So in general, for max 2 CSP, the input is a graph G. For every vertex V, you have an alphabet sigma V, and for every constraint, for every edge, you have a constraint, which is just a subset of the possible assignments to the two vertices. And the goal is to choose for every vertex V an assignment xv by this alphabet and sigma v, such that the maximum, the number of satisfied constraint is maximized. And in this talk, I focus on this graph G, called the primal or Greifman graph of the instance. And I want to restrict it to a class of graphs and ask about the complexity of this problem. Or more generally, instead of relational constraints, we can have valued constraints, so functions which to every possible assignment give you a real number, some value, non-negative finite value, and the goal is to maximize the sum of those values. So let's first discuss what we know about exactly solving such problems. So first, for the problem of deciding whether any solution exists, Grohe, Fintig, and Sigmund showed that this problem is solvable in polynomial time if and only if G has bounded truth. So this is a very interesting exact characterization that, that there is an algorithm here if and only if G has bounded truth. And this shows that CSPs are indeed the right setting. They allow to make such exact characterizations. You might know a more general theorem by Grohe, which considered the homomorphism problem. So homomorphism from a class of structures are solvable in polynomial time if and only if this class of structures has bounded truth up to homomorphic equivalence. So I won't define this here, but the idea is that, for example, bipartite graphs are easy because while they can be very dense, of course, they are all homomorphically equivalent to small graphs, which is K2, and this is what makes the problem easy for them. And this was generalized to value CSP problems recently by Clément Carbonel, Michael Remer, and Stan de Givney. So we know that for exact solving, we have this exact characterization where the crucial definition is bounded treewidth. That's what makes exact solving easy. I wanted to discuss shortly another area where we know similar exact characterizations, namely fixed parameter tractability. The question there is, given a graph G and a parameter K, we want to decide if the optimum is at most K or at least K in time f of K times a polynomial, where the degree of the polynomial doesn't depend on K. Or more generally, given a graph in the formula phi, decide whether G satisfies phi in a time that can depend arbitrarily on the formula, but it has to depend polynomially on G, and the degree of this polynomial does not depend on the formula. And for such problems, there is a very wide theory developed by many people over many years. And two main results of that theory is that for properties expressible by monadic second-order formulas, it is possible to get such algorithms if and only if G has bounded treewidth. And for properties expressible by first-order formulas, this is possible if and only if G is nowhere dense. So there's these two crucial properties of graph classes. One is bounded treewidth, and the other is nowhere denseness. So this leads us to this diagram of different notions of sparsity. So at the very bottom, we have familiar notions of stars, trees, and paths. So of course, these are very sparse and very easy algorithmically. Generalizing stars, we have graphs of bounded treedepth, and then still more generally graphs of bounded treewidth. Of course, you're familiar with planar graphs, and then more generally graphs embeddable in a fixed surface, so graphs of bounded genus. Then there's graphs excluding a minor, and the famous Robertson-Seymour theorem, which says that basically this looks like graph of bounded genus together with some noise of bounded treewidth. Then we have graphs of bounded degree, and graphs excluding topological minor, with generalized those, and graphs excluding a minor. And then still more generally, we have graphs of bounded expansion and nowhere dense graphs, which are crucial in this fixed parameter tractability setting. So nowhere dense is this class and this property which characterizes first order problems, essentially. So here I want to add to this diagram the fragile classes and hyperfinite classes, and to connect this to everything I said earlier. In the end, I conjecture that the Max-CSP problem has a polynomial-time approximation scheme if and only if G is fragile. So I conjecture that fragility is this crucial notion for approximation. So let me introduce hyperfinite and fragile classes. So the idea is to look at where PTASes come from, and the earliest one probably comes from the Lipton-Tarjan separator theorem, which says that planar graphs have balanced separators of size square root n. And more generally, if you have a class of graphs which has sublinear separators, sublinear balanced separators, then you can divide and conquer. So you can divide using the separator, remove the separator from the graph, and recurse into the components. You compute the separator again, you remove it, and eventually you hope to get to constant size components by removing just a very small fraction of edges. So this gets us to the definition of hyperfiniteness. A class of graphs is hyperfinite if for every epsilon, however small, there is a constant, such that for every graph in the class, I can remove a small epsilon fraction of edges to get components of size at most k. And then for such components, I can solve the problem by brute force, and hopefully, because I just removed a small fraction of edges, the optimum didn't change that much. This works for some problems, but it doesn't work, for example, for general Max-CSPs when the alphabet size is arbitrarily large. At least it doesn't work straight from this definition. And moreover, hyperfiniteness implies bounded degree, so it is a quite restrictive definition. However, there still is this general intuition that either we have all of n balanced separators, so sublinear balanced separators, or we don't have such separators, so graphs are expanders in a sense, and then we hope we can encode hard instances on those expanded graphs. So this intuition turns out to be wrong in some ways. So for example, Moshkovitz and Shapira gave counterexamples which showed that it doesn't suffice to have just sublinear separators. They actually need to be at most n over log n in order for this approach to work, so in order to get a hyperfinite class of graphs. Fortunately, there is a better technique known as Baker's shifting technique. So in the planar graphs, many problems have a polynomial-time approximation scheme which works as follows. So you start with an arbitrary vertex, you partition vertices into BFS layers, so by distance from this fixed vertex, and you color them by distance modulo 1 over epsilon. And then just by the pigeonhole principle, you know that one of the colors hits the optimum at most epsilon times. So what you can do is you can try each possible color, remove it, and then if you start with a planar graph, you can prove that the remaining graph has bounded treewidth. So a bounded number of consecutive layers in the planar graph has bounded treewidth. And this means that the resulting instance can be solved exactly, and because we removed the right color, we hope the optimum didn't change too much. So here we don't know which color to remove, but because they're just 1 over epsilon colors to check, we can just check each one by one and get an approximation this way. So this is a very simple polynomial-time approximation scheme which works for many problems. And it works here for planar graphs, but of course people considered whether autograph classes that can be partitioned in this way, so into layers such that a bounded number of consecutive layers has bounded treewidth. And this is known to hold for graphs embeddable in the fixed surface, and more generally for excluded-minor graphs. But there are still examples beyond that. So for example, graphs embeddable in the plane or in a fixed surface with a bounded number of crossings per edge. These will also have this property. And there are also some geometric intersection graphs which are more general and which still have this property, which allows to get an approximation scheme. So generalizing all that, Dvořák introduced this notion of fragility. So a class of graphs is fractionally-treewidth-fragile if for every epsilon and every graph in the class there is a distribution of sets such that removing a random set always reduces the treewidth to a constant, and yet every vertex is removed with small probability. So you have some random way to remove vertex sets such that every vertex is removed with small probability, and yet you always get to bounded treewidth, where the bound depends on epsilon only, not on the graph. So at first this might seem like a complicated definition, but it's a very nice definition which is also very robust. It's more general than all the examples listed above. For example, three-dimensional graphs or d-dimensional graphs of a fixed dimension are fractionally-treewidth-fragile. The proofs for this property are easier. So, for example, the proof that H-minor free graphs are fractionally fragile does not require the Robertson-Seymour theorem, so it's much easier. This definition is also more useful algorithmically than hyperfiniteness. It's easier to apply it to problems such as CSPs. And it's more robust. So, for example, if we replace tree with treedepth, it turns out we get an equivalent definition. And then if we replace those vertex sets with edge subsets, it again turns out that we get an equivalent definition. So these are some of the reasons why I conjecture that CSPs, Max-CSPs for a class of graphs admit a PTAS if and only if G is fragile. So I conjecture that fragility is this crucial notion for approximation. And one of the things we showed is one direction of that conjecture. So we proved an algorithm that if you have any fragile class of graphs, then you get an approximation scheme. Actually, this follows immediately from the definition of the project, assuming you have access to the sets, to the vertex sets you have to remove, or to this distribution of vertex sets. If you have algorithmic access to that, then it's easy to construct algorithms from that. What we showed is that you don't actually need this. Instead, if you just run the Shirley-Adams linear programming relaxations, then some structural properties of fragile classes imply that this very simple algorithm gives you a polynomial-time approximation scheme. So we don't need any way to witness fragility. We just assume that the graph is fragile, and then we immediately get an approximation scheme. For the other side of the conjecture, I think it's an interesting research direction, but we don't know much about this. So, for example, if you have any class of graphs with high girth and which are all free regular, and does this imply that the Max-CSP problem is hard to approximate? So we don't know about this, but studying such problems, we found out a new connection. So we found out that fragility is tightly connected to hyperfiniteness. So it turns out that for a class of graphs that is closed into subgraphs, G is hyperfinite if and only if G is fractionally-treewidth-fragile and has bounded degree. So this connects two definitions which come from different areas of mathematics. And hyperfiniteness in particular comes from the study of amenable groups, graph limits, property testing. And in this area, it turns out that our theorem already implies something interesting, the equivalence of two properties, property A and uniformly local amenability. So this just shows, I hope, that these definitions of fragility, of hyperfiniteness, are quite fundamental. They connect many areas of mathematics, not just CSPs. But back to CSPs, we know that there are polynomial-time approximation schemes for dense graphs. So for example, like in Gray's theorem, we can ask for which classes of structures A does the maximum homomorphism problem admit a polynomial-time approximation scheme. So for example, for the class of bipartite graphs, the problem is again trivial. And it turns out that by extending results of Herrera et al. And Friese and Canaan, we were able to show that in this setting of maximum homomorphism, we also get a PTAS for dense graphs. So for every class of undirected graphs with at least c n square edges, where c is some constant, the maximum homomorphism problem admits a PTAS. So here it's crucial that the input structure are just graphs. It's not that the Geifman graphs of them have many edges. It's the structures, the input structures are graphs, undirected graphs, and they have many edges. If you try to generalize it even just a little bit further, so for example, if you look at orientations of clicks, then these are dense, of course, but it turns out it's impossible to get the PTAS. We proved that the problem is hard for orientations of clicks. But for undirected graphs, it turns out there is a PTAS, and the proof relies, as earlier results, it relies on the Szemerédi regularity lemma, which says essentially that if you have a very large graph, then you can always partition it into a constant number of parts, such that the edges between two different parts behave like a pseudo-random graph of some density. So all you have to do is to remember this density, and then very different parameters, such as the maximum homomorphism number, can be approximated by just looking at the densities. But the approximation here is additive, so we get a plus minus epsilon n square approximation, and this is typical of applications of the regularity lemma. So it is an additive approximation and not a 1 plus minus approximation, so it's not a PTAS in general. However, if we restrict to a class of graphs which has omega of n squared edges, then this additive approximation is a 1 plus minus epsilon approximation, and this means we have PTAS. So this is kind of weird. It's not any structural property, it seems. We just restricted the number of edges artificially so that an additive approximation turns into a PTAS. But it turns out there is a structural definition which generalizes both the clearly structural definitions for sparse graph and this dense result. So let me talk about this now. So the idea is to define the distance between two structures so that two structures A and B are a distance at most epsilon if the answers for those structures are similar. So if the maximum homomorphism number to any other target structure are similar at the epsilon. And then we say a class of structures A is Treewidth-Pliable if all structures in that class are close to structures of bounded treewidth. So for every epsilon there is a constant bound of the treewidth, so that every structure in your class there is some structure B which is close to it and yet has bounded treewidth. And here you should think that bounded treewidth, it's the thing that makes solving the problem exactly easy. So bounded treewidth structures are exactly those structures where solving the problem is easy. So this is a very wasteful definition, you could say. We're just asking for a class of structure where it's easy to solve the problem because, well, simply the solution is close to some graph of bounded treewidth. But first notice that we just assume there exists a graph B. We don't assume it's constructible in any way. And furthermore, we show that there are different equivalent definitions which allow to prove quite a few interesting results. So in particular, this is what allowed us to show that this captures both the sparse case, the fragile classes, and the dense case. So we showed that for any Treewidth-Pliable class of structures, the maximum homomorphism admits a PTAS, and this PTAS is, as before, it's just a linear programmable relaxation, the Shirley-Adams linear programmable relaxation. We show that fragile classes are pliable, so formally for every fractionally-treewidth-fragile classes of graphs, the class of all structures on G, so all structures whose Geifman graphs are on G, this class of structures is Treewidth-Pliable. And this is why the CSP problem, such as Geifman graphs, has a PTAS. And for classes of graphs as structures, graphs that have many edges, dense class of graphs, we show that they again are Treewidth-Pliable, and this is why the maximum homomorphism problem from dense graphs has PTAS. And in fact, in this sparse case, if we only consider the structures, if we only restrict the Geifman graph of structures, then it turns out that the two definitions are equivalent. So class of graphs is fractionally-treewidth-fragile if and only if the class of all structures whose Geifman graphs are in G is Treewidth-Pliable. It's just that Treewidth-Pliability is a more general definition which applies not only to the Geifman graph of a structure, but to the structure itself. And as I mentioned, we were able to show a few more results. So for example, I think it's interesting that if you replace treewidth with different parameters like treedepth or size of the structure or Hadwiger number, which is just the maximum click minor in the Geifman graph of the structure, then it turns out we get equivalent definitions. And this is inherent for approximation, that it turns out that in this approximate setting, treewidth is the same as treedepth, or the same as size, or the same as the Hadwiger number. That is all I wanted to talk about today. Thank you for listening.